Energy is a very broad term. We use the term energy in various different subjects like physics, of course, chemistry, biology, in everyday language. But what we mean by energy in physics is, first of all, energy is a scalar quantity. So that means that it doesn't have a direction, but it can be positive or negative. The unit for energy is the joule, and the symbol for that is just capital J. So some forms of energy that we will discuss are kinetic energy. So kinetic, just like kinematic, has to do with motion. So kinetic energy is the energy that an object has in motion. And the symbol for that is K, or sometimes T or KE. We'll just use K. Then there is potential energy. This potential energy is also an umbrella term for several different kinds of energies that are stored in the system. So, for instance, one type of potential energy is gravitational potential energy. Another one is spring or elastic potential energy. Another form would be electric potential energy. So all of these things have a symbol U, and then you can put a subscript so we can differentiate between gravitational, elastic, or electric. And then there are other types of energy. We're going to be using these mostly for now. Another type that I should mention is heat, and we will talk about that later. Now, one thing about energy is that it doesn't appear or disappear. It gets transferred from one form to another. So we can say that an object that's falling initially, when we're holding it up above the ground, has gravitational potential energy. As it's falling, its gravitational potential energy is decreasing while its speed, so kinetic energy, is increasing. So energy is converted from one form to another. So let's start writing out the equations for these different forms of energy. So kinetic energy is 1/2 mv squared, where m is the mass of the object and v is the speed of the object, so we square that. Then there is the gravitational potential energy, and that would be mgh. M again is the mass of the object, g is the acceleration of gravity, and h is the height above a ground level of gravitational potential energy. So whenever we're dealing with the gravitational potential energy, we express it in terms of the zero level gravitational potential energy. So if I look at a hill like this, and I say, well, this point is at a height h above the ground level, I am assuming that this is the ground level, and at the ground level, potential energy is zero. So then the object would have potential energy mgh, h above ground level. All right, the spring potential energy is 1/2 kx squared. So k is the spring constant, and it's a function of the spring, the size, the material the spring is made of, things like that. And x is how much the spring stretches from equilibrium. So again, we have to express the spring potential energy relative to where the spring potential energy is zero. So x is stretch from equilibrium. So let's say that we have relaxed spring here, and let's say that we are stretching it by applying a force to it. Then the energy in the spring has to do not with the original length of the spring, not with the final length of the spring, but with the difference between them. So this will be the x. That is how much the spring stretched from equilibrium. Now the spring can also be compressed. And then again we have the spring potential energy is 1/2 kx squared. All right, we will talk about electric potential energy and heat in a later video. So now let's see how these different forms of energy convert from one form to another. So let's say that we have an incline, and then I'm going to put a spring at the bottom here. Let's say that that's ground level, and let's say that there is no friction along this path, so mu equals 0. Let's place an object up here and say that its initial velocity is 0. So we're holding that object at rest, and then we will let it go. So since gravity acts on it, it will make it go down that incline. Since there's no friction, there's no static friction either, so the block will just slide down. So initially, the block will be a height h above the ground level, so it will have potential energy, gravitational potential energy. Then, as the block is sliding, it's picking up speed. So at this point, the block will have speed v1, and it will be a height h1 off the ground. So at this point, the block has u grav 1 plus kinetic energy 1. So the gravitational potential energy that we had initially was transformed into gravitational potential energy plus kinetic energy. So gravitational potential energy decreased while we picked up kinetic energy. Now let's say that down here, the block will have a velocity v2. The block will be on the ground. I know I didn't draw it directly on the ground. I tend to do that. I want to see my object as being separate from the incline, so I don't draw it directly on the ground. But what I mean here is that all of the energy that the block had initially was transformed into just kinetic energy. So since the block is at ground level, mgh is going to be 0, and all of the energy was transformed into kinetic energy. Now, I'm going to redraw this ground level. So initially, the block was moving with velocity v2 when it first touched the spring. So v2. Then the spring compressed, and the block came to a momentary rest. So now when the spring is compressed and V final is 0, then all of the energy here is going to be in the spring, in the compressed spring. So to summarize this, we had mgh becoming mgh1 plus 1/2 mv1 squared, which then became all 1/2 mv2 squared, which became 1/2 kx squared. So in this example, we had energy transformed from potential energy, gravitational potential energy, eventually into spring potential energy. Now, what is nice about this chain of energy transformations is that I chose no friction on the plane, so that means that all of these situations, in all of these situations, the energy is the same. So we had the same amount of gravitational potential energy at first as we did in the very end. So this is a way of showing that energy is conserved. Now, we have some things called conservative and non-conservative forces. So, conservative and non-conservative forces. So, if we're dealing with conservative forces, it probably makes sense to you that a conservative force will produce conservation, or will facilitate conservation of energy, whereas non-conservative forces will not. Energy will not be conserved when non-conservative forces act. There are other terms that mean the same thing. So a conservative force is a path-independent force. And a non-conservative force is a path-dependent force. So what that means is that if I'm dealing with a path-independent force, let's say that I have an object here and I want to move it to that location, and I will take a path that goes like this, or I can take a path that goes straight across. Then the work that I do going from point 1 to point 2 is the same. So work is the same along both paths. Now for a path-dependent force, so I start at this point, end up at that point, and here I go with squiggles as opposed to going this way. And with a path-dependent force, the work is different. So we can write an equation that says that work done by non-conservative forces is equal to change in energy. All right, so what do I mean by energy? So energy is total energy. So it is the sum of all forms of energy acting at a certain place. And I shouldn't say acting, because that would imply a force. So all the forms of energy at a certain place. How about that? So we could have as the total energy kinetic energy plus potential energy. Let's just leave it at that. Then work done by non-conservative forces would be final energy minus initial energy. So I can say that would be kinetic energy final plus potential energy final minus kinetic energy initial plus, wrong letter, plus potential energy initial. Okay, so that's how I would write the right side of the equation. Now, work done by non-conservative forces. So actually there are fewer conservative forces than there are non-conservative forces. And one of the most common non-conservative forces we will deal with is friction force. So the work done by friction force is friction, so that's kinetic friction because we need the object to be moving, times the displacement times cosine of the angle between friction and displacement. So if the displacement is in that direction and friction will retard the motion, so it's going to be in this direction, then the angle between them is 180 degrees. So then we have cosine 180, which is -1. So work done by friction is going to be negative Fk times d. So putting all of this together, we would have for a system in which there is friction, negative Fk d is going to be kinetic energy final plus potential energy final minus kinetic energy initial minus potential energy initial. Now, in the absence of friction, which is what the example was before, there are no non-conservative forces acting, so that means that we have conservation of energy. So in the absence of friction, work done by the non-conservative force of friction is 0, so we have 0 equals delta total energy, which is energy final minus energy initial. So that means that the total initial energy was converted into final energy with no energy loss. Now, another type of energy that we can think of that will cause energy to be dissipated is heat. So where there is a friction force, there is work done by the friction force, and you can also think of the heat that's dissipated, and that's another form of energy. Another concept is called the work-energy theorem. And that says that the net work is equal to the change in kinetic energy. Now, what does net work mean? Net work is the work done by conservative forces and work done by non-conservative forces. So how does this equation differ from the one we have up here? Well, it doesn't really. If we actually just took out the work done by non-conservative forces from this equation, we would figure out that the work done by conservative forces and the change in kinetic energy would be equal to the work done by non-conservative forces. So there are really two ways of looking at this equation. Let me rewrite these two. So we have work net is change in kinetic energy, and then work done by non-conservative forces is change in total energy. And I said that I would use K for kinetic energy, so I got rid of that E over there. Okay, so these two equations are really equivalents of one another. Just pay attention to the subscript. We have non-conservative forces here, and we have net work, so that's the work done by friction and weight and all the other forces that act on the system. Here we only have the work done by the non-conservative forces, like the force of friction. All right. Another concept that's related to this is that of power. Power is work divided by time. So if work is change in energy, then it's change in energy divided by time. The unit for power is the watt. So it's in watts, and the symbol for watts is W, not to be confused with the W for work or the W for weight. Let's rewrite this a little bit. So power is work divided by time, and work is F d cos theta divided by time. So distance over time is velocity, so we can also see power as force times velocity times cosine of the angle between them. So that's a different way of writing power. All right, so big concepts. Kinetic energy is 1/2 mv squared. Potential energy, gravitational, is mgh. Spring potential energy is 1/2 kx squared. Then work done by non-conservative forces is change of total energy. So pick initial energy and final energy, write down all of the different types of energy at the initial point, write down all of the energy forms at the final point, and then figure out what the work done by non-conservative forces is. If no non-conservative forces act in the system, then the work by non-conservative forces is 0, and then you have conservation of energy. And then the last but not least concept is power is work divided by time, and that can be of course expanded to change in energy divided by time, or force times velocity times cosine theta.